Good morning and welcome to the last day of our workshop where we have Giulia Cereda from joint PhD between University of Leiden in mathematics and forensic science in Lausanne. And she'll be talking about the likelihood ratio assessment for the rare type match using a Bayesian nonparametric.
Thank you. So good morning to everybody. So I would like to talk about the likelihood ratio assessment for rare type match with Bayesian nonparametric method. It's a rather long title, but actually there are three main concepts in this title. So we have likelihood ratio assessment, the rare type match case, and then Bayesian nonparametric method. And I would like to spend few words to introduce these three concepts to you. So the likelihood ratio assessment. So when we have a crime case, for instance, we have a murder and we find a DNA stain on the crime scene. There may be two hypotheses of interest, one from the prosecution and one from the defense. And for instance, at the source level, the prosecution may believe that the suspect left the stain, and the defense may believe that someone else left the stain. So the forensic scientist has data which he would like to exploit in order to kind of discriminate in some sense between these two hypotheses. And I would say that the data can be divided into evidence. So evidence is data directly related to the case. For instance, in this murder case, you find this DNA trace, you look at the profile, and you see that this DNA trace matches with, so the profile is the same as the suspect profile. So this is data which is directly related to the question of interest. On the other hand, you should have also background data, which is data that is not directly related to the two hypotheses to the crime, but will help you to assess the unknown parameter of your model. Typically, in this case, the unknown parameter is the rarity of the profile of the suspect in the population of possible perpetrator. And you may use a database which is a sample of DNA profile from the population of possible perpetrators. So this database has been probably collected before the crime, so has nothing to do with this case, but still you will use this data to, for your case. So in the end, you have to calculate the likelihood ratio, which is the ratio of the probability of observing your data, so evidence and background, under the two hypotheses of interest. Okay, now so in this research I want to focus on likelihood ratio assessment for a specific case, that is the rare type match case. So in particular, I just want to warn you that many times I will use the word DNA profile. What I mean is a YSTR profile. So I'm focusing on YSTR data. A YSTR profile is a list. For instance, I'm using just 7 loci on the Y chromosome. So it's a list of STR allele that you observe on 7 specific locations of the Y chromosome. So I'm using YSTR profile. And when you use this data, it typically happens that yes, you have the match between the crime stain profile and a suspect profile. But when you look at your database to try to assess the rarity of this profile, you realize that actually this YSTR profile is not in your database. So if the database, for instance, is big, it's likely that it's a rare profile in the population, but you really need to try to assess how rare it is. So I just want to show you, this is a Word database of almost 19,000 individual YSTR profile. And by looking at 7 loci, you see that you have 3,000 distinct profiles, but 2,000 of these appear only once in the database. So here you see the plot. This is the log scale plot of the ranked frequency of the profile in the database. You may see there are few profiles that are kind of common in the database, and a lot of profiles that appear only once. And the log scale plot shows this nice behavior. So it's very likely then when you observe the next profile, it will be new. It will be adding one to this long list of singleton in your database. So now, the third part of the title of my presentation was Bayesian nonparametric model. What is a Bayesian nonparametric? So, as a Bayesian model, a normal Bayesian model, so you have data, and then you have, this is the parameter of your model, P, and here the data also depends on the hypothesis of interest, but the point is, we want to be Bayesian, so we will put a prior distribution on P to describe our uncertainty over it. And being nonparametric means that we want P to be an infinite dimensional parameter. So it's kind of a Bayesian model, but with an infinite dimensional parameter. In our specific case, you will see that our parameter will be an infinite vector containing the frequency of each profile, the unknown frequency of each profile in the population. I want to anticipate the final result of this research. So by choosing a prior for P that depends on two parameters, alpha and theta. So we want to be full Bayesian, so we will put an hyper prior over alpha and theta. Okay, so just let me explain. When you have a prior over P, and this prior has two parameters, we will call them hyperparameter. And so the prior that we put over these two parameters will be called hyperprior. So the point is, with the choice of prior that we made, the assumption of our model, and the data reduction, which I will explain you very soon, we obtain that the likelihood ratio can be written as 1 divided by the posterior expectation of this simple function of the two parameters alpha and theta, given the data, actually the data reduced, but you will see what I mean very soon. And moreover, what is really nice here is that if the hyperprior for alpha and theta is pretty uninformative, we check and we show, for instance, with the word database that I have, with the word data that I have, that we can easily and safely approximate this likelihood ratio by plugging in the maximum likelihood estimator for the two parameters. So it's not only an easy formula, it turned out that it's also very easy to computate. So the MLE calculation is done by R, but it's really fast. It's not heavy computationally. So this is kind of the final result which I want to get, which I want to show how to get. And okay, so I just wanted to give you a brief overview on the final slide. So, yeah.
So in your expectation, what is random? Sorry, I got a bit confused.
Yeah, it probably is not well written, but the thing is that you have alpha and theta, which are treated as random variable. So you are talking about the posterior distribution of these two parameters given the data. Yeah, I should have
the expectation both with respect to alpha and...
Yeah, I should have written them with uppercase, so you maybe... Yeah. So, yeah. Okay, now I think it's time to talk about the prior that I choose for my parameter P. And one way to describe it is to talk about the two-parameter Chinese restaurant process. This is a stochastic process with a rather folkloristic name, but it's a stochastic process that depends on two parameters, alpha and theta, that help to satisfy these two conditions. And actually, what it does, it describes the sitting plan of customers entering into a restaurant with an infinite number of tables, each one infinitely large. I guess this is the reason why they call it the Chinese restaurant process. I mean, I cannot see any other reason why. So let's say that y1, y2, yn is the sitting plan, meaning that it describes at which table each customer decides to sit. So of course, the first customer enter into an empty restaurant. So with probability 1, he will sit to the first table. So with probability 1, y1 is equal to 1. Then the second customer has two choices. He can either decide to sit with the first guest customer, so they could share the table 1, and this happens with a probability that is proportional to 1 minus alpha, or he could choose a new unoccupied table. So he could go to table 2. And this happens with a probability which is proportional to theta plus alpha. Well, then at time n plus 1, so when the n plus first customer enter the restaurant, n people have already seated, so they sit according to, y1, yn, to k different tables. So at time n plus 1, k table have been created, and the n plus 1 customer has several choices. He could either choose to go to a new table, so the k plus 1 table, with probability proportional to theta plus k alpha. So you see exactly this probability, but here k was equal to 1. So he could either choose a new table with probability proportional to theta plus k alpha, or he could choose one of the already occupied table. And this will be done with probability which is proportional to ni minus alpha, where ni is the number of people that sit at that table. So he has k plus 1 choices. Okay, so imagine that you can observe the customer entering to this restaurant for an infinite long time. At the end of this infinite long time, you will have, you can look at the relative number of people which sit at each table, and you can decide to order these relative numbers into a vector p. And this is, for instance, what you may see. Like, this is the table which is which has here we have the more, let's say, the more popular tables, and here you have the table with few customers. Okay, but this is when you look at this process once. Then imagine that you want to look at it again. You will obtain something different, and so on. Every time you run this process, you get to a different distribution of the customers into the table. So this vector p that you observe at the end of the time as a distribution, first it's an infinite long vector. It's sorted in, so the first number are the biggest one, and it has a random distribution, which is called the two-parameter Poisson Dirichlet distribution with parameters alpha and theta. Well, this is the distribution that I will choose for the parameter of my model for YSTR data. Okay, so I just want, before going into the detail of the assumption and the reduction of the data of my model, I want to give you some notation. In this talk, we will denote by square bracket n the set of integers number from 1 to n, and as pi n the partition of this set. So just a little example is n is equal to 10, then the partition of the integer number from 1 to 10 is a set of subset of this initial set, these joints, and the union of which form the initial set. So in particular, we will use random partition, which will be denoted as uppercase pi n. So let me start by the assumption of my model. The first assumption is that there are so many different DNA types in nature that you can consider them as infinite. it means that I can use for my model an infinite vector containing the frequencies of this profile. So for instance, this is also, I decided to order it, and P3 is, for instance, the frequency of the third most frequent type in nature. P1 is it's the frequency of the most frequent type in nature, and so on. And I choose the two-parameter Poisson Dirichlet distribution, which I just showed you, that you obtain with the Chinese restaurant process, as prior for P. And then the second assumption is that, so as I told you, a YSTR profile is a list of some STR alleles that describes number of repetitions on different portion of the Y chromosome DNA sequence. The thing is that I would like to consider each profile as a category. So I don't want to use the information of the particular list of numbers that form my YSTR type. So Calibe yesterday described these models that are based on this assumption as multinomial model. Like we throw information, the information about the exact number inside the sequence. We don't put any topological structure, and we just consider the category. So now DNA types is the same as colors. So this assumption is important because it allows me to treat my database, which contain lists of YSTRs allele, as, I mean, I can just throw all this information inside this list and just consider the colors, like what is equal to what and what is different to what. It means that my database can be actually reduced to a partition. I can just consider, so instead of having all this information here, I throw them and I just use the partition of the indexes from 1 to 10 made of the equivalence classes obtained by the equivalence relation to have the same DNA type. So this is a rather long sentence. Maybe I should give you an example. The idea is that from this database, I only retain this partition. How is this made? You see, for instance, 1 is alone. Why 1 is alone? Because the first person has an haplotype that nobody else has. 3, 5, 6, 8, 10 share the same haplotype. So they are in the same class of my partition, and so on. So this is how I reduce my background data, my database. But actually, my data is not only made of the database. Of course, we only need the evidence, and the evidence is 2 new observations. So we have the database, background data, and then we have the database of the suspect and the database of the crime stain. So actually, the database of size n is reduced to the partition of the integer from 1 to n. The data is made of the database and 2 new observations. So my entire data can be reduced to a partition of the set from 1 to n plus 2. Not only, in the rare type case, if this is the partition of my database, as in the example, the partition of n plus 2 will have a particular form that is 11 and 12. So the suspect type and the crime stain type, they are the same, so they are in the same class, and moreover they form a class by themselves because we are in this rare type case, so nobody else in the database have the same haplotype.
Under the prosecution hypothesis, we've only seen 1 new observation.
Well, but you can say that you see 2, but the probability for 12 to be in the same class of 11 is 1. So
will that be included in your modeling?
Yes. When I will describe the probability of the data given P, you will see that according to the prosecution. So what you point out is pretty important.
Each cluster you have, like 11, 12, they all have the same genotype.
Yes.
So that, yeah, I'm just trying to.
Yeah, but what he's saying is that you can see it in a different way and say, okay, according to the prosecution, you only have 1 more observation. But you can always also say that you have 2 observations which are the same, and then according to the defense, there is some probability for 12 to be equal to 11, which is lower than 1. According to the prosecution, 12 has probability, so it for sure will go in the same class. Yeah. So actually the prosecution and the defense will agree on the distribution of this partition up to 11, and then they disagree on 12. So now the data can be seen as a random partition of the integer from 1 to n. And this is my model. So we have our random vector here, which is given a Poisson Dirichlet prior. We have hyperpriors alpha and hyperparameter alpha and theta, which I will give to which I will give kind of an informative hyperprior. And then you see the data depends. The distribution of the data not only depends on p, but depends on h. How? This is the likelihood ratio, of course. It's the probability of observing my data under HP divided by HD. What Professor David was saying is actually this. So if you have the partition obtained with the database, then you observe the suspect type, and you have this kind of partition here. And when you observe also the Kreinstein type, you have this. Sorry, here it should have been n, not n plus 1. This is n. The defense and prosecution disagree on the probability that this and this are in the same class. For the prosecution, this is a sure event. For the defense, there is a certain probability for n plus 2 to go here or in another of the other class. So this is the point. So actually, you can write the model in this way. I mean, this part of data, the distribution of this part of data given p does not depend on h. So this is the part of distribution that depends on h. So this entire part, this data here, has a distribution that depends on h. So, okay, so just let me go. The thing is, I would like to calculate this likelihood ratio, and to make it simple, I can make use of a lemma. So given 4 general random variables whose conditional distribution is described by this Bayesian network, it always holds that the likelihood for h given x and y. So you see here you have the part of the data. If you think about our model, here you have the part of the data whose distribution is agreed on by prosecution and defense, and here you have the part of the data whose distribution depends on which hypothesis you believe is correct. And it means that the likelihood for the hypothesis given all your data, it's always proportional to the posterior expectation of this posterior density given the data, but only the data that is agreed on by both of them. So here what is random is A. So I'm talking about the average over the posterior distribution of A given X. And of course, we can use it in our case because we have a model which looks like that. So the conditional dependencies are hold. And so I can say that the likelihood for the hypothesis given the data up to n plus 1 and the data up to n plus 2 is proportional to this posterior expectation. This can be used for the likelihood ratio because the likelihood ratio, it's the probability of this data, but given this is deterministic. So I can just add this inside the parentheses, and then you get to the ratio of this likelihood. We can apply the lemma, and this is just the ratio of these two posterior expectations. Now let's look at the first part here, so of this posterior density. Given HP, and given the distribution up to n plus 1, the probability of observing the partition up to n plus 2 is 1. Because for the prosecution so they believe that it's the same person, the one that left the stain and the suspect, so you will have the same DNA type, so the probability that you see n plus 2 in the same class as n plus 1 is 1. Now, what is the probability of what we have in the denominator? So I would like to write what's the probability that if you see a random, so the YSTR of a random person, which is not the suspect because we are under the defense hypothesis, this will go in the same class of the n+1. Well, we can use a nice result about the Chinese restaurant process, which says that if you look at the partition that you get from your database, so I mean a distribution that you get partitioning an IID sample from P, and then you look at the partition that you got when you look at the sitting plan of n customers inside this Chinese restaurant process, these two partitions have the same distribution. So you can obtain exactly the partition distributed in the same way by observing an IID sample from P and partitioning the results, like partitioning the database, or letting n customer enter your restaurant and partitioning the table according to how many people sit at each table. So it means that if I want to know what's the probability for, sorry, I didn't want to point that. So if you want to look at the probability for the YSTR at the n+2 observation to be equal to the YSTR profile at the n+1 observation, you can use the probability for the n+2 customer to choose the same table as the n+1 customer. And this probability is 1 minus alpha divided by n+1 plus theta. And this is how we get to this nice formula which I show you at the beginning of my presentation. So, but we still have this issue of how to calculate this posterior expectation. So let me just reparameterize everything and using phi, which is now n times the quantity which I have here inside. So I can write the likelihood ratio as n times divided by the posterior expectation of phi, given the data up to the observation n+1. And then remember that I told you that we choose an uninformative prior for alpha and theta. So the same for if I consider phi and theta. Phi is just a function of alpha and theta. So
Sorry. I mean, a uniform prior, if that's what you meant, I don't know, for alpha and theta, wouldn't give a uniform prior phi and theta, would it? It's a non-linear transformation.
Yeah, but
I don't think there is such thing as an uninformative prior.
like a smooth prior, something which is kind of flat around the MLE. This is what I meant.
So, are you arguing that the likelihood in terms of alpha and theta is highly peaked, and therefore we don't have to be too fussy about the prior?
Yes,
It's peak but also smooth, right? So
that's what she's saying.
Yeah.
That's what she wants to say.
That's what you'd like to say. You've got evidence for it.
no,
That
yeah.
would depend on your prior, wouldn't it?
No, I'm talking about the likelihood.
Oh, yes, she'll show you the evidence in a moment.
So we agree that now we can say that this is kind of proportional to this,
Okay.
and I don't need
Take
to
it
multiply.
going on,
Yeah. And then I don't have to multiply by the prior here, okay? So, of course, to have this posterior expectation, I'd like to know what this look like. Let me show you what these look like. So, this is for using a this YSTR database with 18,000 individual. This is how it looks like the log 10 likelihood for my observation, given the two parameters. So this is theta and this is phi. Okay. Now look at how it looks like a normal distribution, center in the MLE, and as sigma metrics we have the inverse of the Fisher information. They are pretty similar, right? So this is really nice because if I want to know the posterior expectation for phi given the data, I can just use the MLE for phi. Because if you look at, because this is kind of a Gaussian contour plot. So in the end, this allow me to write the likelihood ratio, to kind of approximate the likelihood ratio as this formula here, which is what I wanted to show. And I believe it's a nice result. Easy, simple to computate, and moreover, let me show you some comparison. When you just use the Dutch database from the entire 18,000 individual word database, you have 2038 profile, YSTR profile from Dutch male people, and so this formula, which I just show you, gives you a like ratio of 5,000, and I wanted to compare it with another formula that I got by using a similar reduction of the data. This is called the generalized good method, also for rare type match, and they are pretty same, close one each other. Then if you look at Brenner method and the augmented database count method, they are kind of less than the half. And I would say that actually this is kind of based on nothing. This is, it's not clear. This is not clear because if you, I couldn't manage to realize what's based on reading the paper. And for these two, at least, I know the logic behind it. And yeah, so, okay, this was what I want to show you. Thank you.
So we have plenty of time for discussion. We have already started. So any questions?
Just a comment, Giulia. I think Buckleton's taken a great deal of time to try and understand what Charles is to do, and has written it up in the latest version of his book.
Okay.
I wouldn't want to bet money on that, but I'm fairly sure he's done that.
Okay.
But I'm on good mates' names now, so which is not an easy thing to do.
Roman?
This could be complete stupidity on my part, but maybe I misunderstood something you said about the defense hypothesis. I think what you said was that the n+1 and n+2 profiles were the hypothesis they were not in the same class, whereas surely what you meant was that they were a singleton rather than a duplet. Sorry, they were duplet rather than a singleton.
Mm-hmm.
That's different from saying they're not in the same class.
If I say that they are not in the same class, I was wrong. That's not what I wanted to say.
That's okay.
Okay. So actually, they are in the same class because that's what we look. That's what we observe. It's just that the defense and the prosecution have different explanation on why they are in the same class.
Okay, I thought, okay.
Okay.
Because it could be. You could have a defense hypothesis that they weren't in the same class, but then, of course, you're disputing the fact that they are actually the same profiles.
Yeah, they are not using what they observe. Yeah. So.
Just a question. I'm not expert of this, but are these methods equally likely in the sense that you consider equally reasonable? And
the first two?
Yes, and in this way, given these results, which number would you provide to a court, for example?
So, first of all, one may be tempted to compare this with the true likelihood ratio, like you make simulation and you say, okay, what it is compared to 1 divided by the p, the true p. So you pretend you have a big database that is your word population, then you look at a sample like the Dutch, and then you say, let's compare this with 1 divided by the frequency in the entire database, pretending it's your entire word. But these two methods are based on reduction of the data. So there's no way to compare them with some ground truth because they are trying to assess different likelihood ratio. If I have to, so the generalized good method, it's even simpler because you see it's just n times the number of singleton. Sorry, I haven't explained it here, but it's like it's n times, so the size of your database, and then here n1 is the number of singleton in your database divided by twice the number of duplets in your database. Here you have a problem, for instance, when n2 is 0, you don't have duplets, so you see weird stuff here, infinite likelihood ratio, and this is exploiting less of the data because it's only using from your database the number of singleton and the number of duplets. The Chinese restaurant method, at least the alpha MLE estimation, is using more information from your database. So I don't know if I have answered your question, but I kind of think that I rather prefer this, maybe because it's what I've studied last, I don't know, but yeah, I think this is more, first of all, it's more funny to work at because you have all this Chinese restaurant stuff, but if I have to use it, I kind of think it's better to use as much as possible from your data. And this is using more.
Roberto first.
Yes, when two YSTR profiles are different.
Sorry, I couldn't hear you.
Yes, I think I've been talking too much lately. I have no voice left. When you have two YSTR profiles, some of them are only one STR different, that could come from a mutation of one profile. So when you have two different YSTR profiles, some singletons are more different than others. So the question is, can this methodology be extended to consider the mutation rates?
I don't know. I haven't. I actually deliberately decided not to look at the distance, like any topological structure, how many alleles are different or not. I just decided to consider categories. So for me, if two profiles differ from one allele, for one allele, they are different. I don't use how much close they are or how much distant they are.
With the bigger database that you mentioned at the beginning, did you look at the differences in the four methods? What are the differences in that case? So you got that result?
I don't have it now. I actually don't remember it. So, but I could easily. It's released, so I can tell you in 10 minutes what it is.
Then Stefan.
Yeah, well, I don't know. A wild shot to the answer whether you can do it is, of course, the Indian buffet instead of the Chinese restaurant, which actually tries to describe clustering. So in that sense, that some of the different species, if you like, will cluster and look like each other, and others will not. Anyway, that's on the side. But my real question is how many triplets do you actually have in that database there? I mean, you're saying you're using much more than the singletons and the duplets, but you might not have much more than that. And I think the rest of it, what you use, might actually just be in the prior, really, and in a certain sense, therefore, just imagination.
So I can. I mean, I have. Sorry, I should have put the entire partition here to show you the data. I don't remember. I think I have kind of. So it was like. I don't remember how many triplets I have, but I believe for this database at least I have some triplets, and also I have.
But I mean, the vast part of the database must be singletons.
Yeah.
So in that sense, whatever method you're using, you're basing it more or less on the singletons.
Yes, and that's why we get to similar results.
Yes, you get similar. So the question is, how sensitive is it to choice of the hyperparameters, for example?
I don't know. I haven't tested.
And or any other non-parametric model for the P's?
At the moment, I don't know. I haven't tested it with other non-parametric priors.
David has a question.
Just partly repeating what I said when we had the YSTR talks yesterday, but I find all of these class of methods to be unsatisfactory because they worry about the relatively unimportant aspect of the problem, and the much more important is the clustering of Y haplotypes geographically and in social groups due to the population genetics and shared ancestry. I mean, none of that's represented here. Even the augmented database method is typically far too overstating the strength of the evidence. So the fact that you're going even further makes me worried. But also, it doesn't take into account at all of these issues, which I really think to get the Y problem, Y chromosome issue right. I mean, this may work well for other rare types, but this important thing that I was talking about, if you go back from a particular Y chromosome to the father and the grandfather, and then think about all the descendants of that individual and how they're distributed, I think that has to be taken into account somehow. And actually, the Chinese restaurant method is a population genetics model. It is used. I think alpha has a relation to the mutation rate. Is that right? And,
yeah. Well,
and
for instance, if you put it alpha equal to 0, you get to the U in sampling model.
Yeah.
So
Okay.
there are relation to.
Yeah. So it does have, but it's still, even then, it misses what I think is the most important part of the problem.
Sandy had a question?
I guess a question and comment. The comment, excuse me, it's just that couldn't you take say, divide your database into 2 random halves and then use the first half to estimate the alpha and the theta and then see how you're doing in the second half?
Yeah, that's.
a way of trying to see whether your model is empirical.
Yeah.
The question is if you could specifically say what the uninformative prior is, especially for the theta.
I cannot hear you, sorry.
Can you specifically say what the uninformative prior is, especially for the theta?
Well, I don't choose any uninformative prior. I'm just saying if it's smooth over the MLE stuff, it doesn't matter. So I didn't choose a specific prior for this case. I'm just saying whatever you choose, if it's uninformative enough.
Well, then it seems to me you do want to explore that a bit, because in terms of guidance for someone else, if I were to think about using this method, I'd want to know, if I have a database of 100 or 1,000 or 10,000 or 25,000, at what point does the approximation become set in? Right? I mean, you're in effect making an asymptotic. you're relying on asymptotics, but don't you need to have some sense of when the asymptotics set in?
I'm sorry, but I couldn't hear. I didn't dare to tell you. But can you just come a little bit further?
You're making an asymptotic statement, right? Or depending on asymptotic results. But the question is, when does how large does n have to be before the asymptotics set in?
Well,
You're using the joint normal distribution,
yes.
which is a limit theorem
Yes.
with 2 MLEs. And all Professor Isabella is asking is, how have you checked the sample size? To do the normal approximation, you need a certain sample size.
For instance, I tried that. So when you
You're not using a normal approximation.
Well,
She's pointing out that the likelihood is very beautifully symmetric, and so if the prior is flat over that same region, the posterior expectation will be close to the posterior, the value at the posterior mode.
But if n is 10, that's not going to be the case.
yeah.
Will your likelihood still look like a nice
For instance,
normal
with the database of this Dutch data, because the plot I show you was with the word 18,000 individual, but just yesterday we checked it with this Dutch database, 1,000 individual, and still the approximation looks good. So 2,000 is safe. Then I could check with smaller databases.
Yeah, it seems that the reason I'm just focusing on the size is relative to what Professor Baldwin was saying. Suppose I have a crime and I decide that only the Turkish immigrants are sort of the relevant population, and my database has 20 Turks, then I have to start worrying about the asymptotics.
Yeah.
So as soon as you do start worrying about this fact of looking at small subpopulations, your database size is going to shrink.
I don't know what to say because I haven't tested on 20 people. So I just show you what happened with 2,000 and 1,800. So probably there's more to do here.
We have to slowly wrap up, but I have 2 more questions. One, Amke, and then mine.
Oh, good. Thank you for your very nice talk. Just have, I think, a short question. So could you say why you choose the Chinese restaurant prior for the P distribution?
Well, why? I kind of don't remember. I remember I was reading on this nice process, and then I was talking about it with Richard, and chance. I think it was more of a chance, but now there is this. Just 3 days ago, we look at this. I look at this paper where from Stand Disabled that says that. I mean, if you just the Chinese restaurant process is like the how can I say? So it under two conditions. Like for instance, that the first customer choose a new table only based on the number of tables which have already been formed, and not how many people sit at each table, and also that they choose a particular table only already occupied only regarding the number of people in that table and not the number of people at the other table. Then the kind of choice that you have for your Bayesian nonparametric prior, it's just the Chinese restaurant. But the reason why we choose that, I don't know. I think we decided to test it, and we saw that it looks good, and this approximation works fine. So you don't have much problem with the parameters.
So this because it has some meaning in population genetics. So perhaps I thought there was some relation to that.
Well, yeah, but that's not how it started. Then I kind of first studied that, and then I realized that after it has genetical interpretation and stuff. So yeah.
A very quick comment from my end.
I was just wondering, when we report YSCR matches, we would make very clear that everyone in the male lineage that you described would have exactly the same Y profile. But then we would still report something about the frequency, and we're sort of struggling with what to report. And if you would first make that clear that everyone in the same male lineage has the same Y profile, and then we would like to say something. Well, if he's not in this lineage, what's then the probability that he sort of has the same profile? And maybe then I'd quite like this method actually.
So, I'll just quickly say I agree that that's right, but I think the first one is so much more important that needs that it's more important to quantify that.
So we emphasize that really.
Right, let's thank Giulia again. And see you